Welcome, everybody. Thank you for joining us today for our NESI pre-conference webinar for the Building Energy NYC conference. Today's session is presented and sponsored by NYSERDA and is a discussion of thermal energy networks. We are 2 weeks away from the conference, which is on Thursday, September 15th in New York City. We hope to see many of you there. And without any further ado, I will hand it over to today's speakers from NYSERDA, starting with Sue Doherty.
Thank you, Ben. Here, I'll take over screen share here. All right, so my name is Sue Doherty. I'm a senior project manager on the clean heating and cooling team at NYSERDA, and I manage our community heat pump systems program, where we're working with solution providers to study the feasibility, design, and install community heat pump systems throughout New York State, otherwise known as thermal energy networks or district thermal or clean thermal energy networks. I'm also joined by a couple of participants who will be presenting after me, Raymond Johnson from EcoSave and then Tony Amos from Endurant, and they'll talk about some of the projects that they have underway through Pond 4614. So if folks have questions and they want to put them in the chat after we've all presented, we'll go through and if we have some time and answer the questions that are in the chat. So thank you for the opportunity to present today, and we'll get started. So we know that we have over 6 million buildings in New York State, and in the building sector, the primary source of emissions is heating and cooling. And we know that if we install heat pumps, those are a method to decarbonize heating and cooling in New York State. So if we want to reach scale and meet our emissions reduction goals, we'll have to move a little bit quicker than building by building and start addressing decarbonization of heating and cooling at a community level. And one way to do that is through clean thermal energy networks, which is depicted in the icons up at the top, where you can see a transition away from each building addressing their individual thermal needs to an entire community being addressed with a network of piping. So we're working with our utilities and municipalities and experts within the field, like the folks who will be speaking after me, to address building heating and cooling at a community scale. This will be a lot of work. Through the process, we'll also be creating good trades jobs, good high-paying jobs, and in the process, lowering the operating costs for our end users as well to heat and cool the buildings. So I talked about this briefly in the last slide. What we're talking about with district-style heat pump systems or thermal energy networks is within a cluster of buildings, networking those buildings together with pipes so that we can share thermal resources. So on the left, you can see each building is in this picture is using ground source heat pumps in order to heat and cool their buildings. But we have reason to believe and evidence to support that if we connect these buildings together, we can achieve heating and cooling more efficiently. One building might be in cooling mode and one building might be in heating mode, so that heat being rejected from the building that's in cooling mode could be used by another building. Also, by connecting these buildings together, they can share the same thermal resources. So when is this, when should one consider a district style heat pump approach? These are examples up here at the top of when you have a diverse set of heating and cooling loads and you connect those buildings together, you're able to share the heating and cooling among those buildings and bring down the overall energy usage. Another thing to consider for a district style heat pump system is proximity to a thermal resource. So having open space in the right conditions to drill boreholes so that you can install geothermal. Another thermal resource that could be used is the wastewater. Or if you're close to facility that is expelling waste heat, such as a data center or an ice rink, you can use the waste heat from that facility further down the line in another building that requires it. Surface water is also a great opportunistic thermal resource. So this is what NYSERDA is doing to support community heat pump systems. We have competitive solicitation, PON 4614, where project sites and solution providers can study the feasibility of a district-style heat pump system, and also perform a detailed design and eventually build the system as well. These are the eligibility requirements for the program. In order to meet our classification of a community heat pump system, there has to be at least 2 buildings on site and comprise at least 40,000 square feet of conditioned space or more, or 10 buildings, or a minimum of 10 buildings, which could be 10 residential size buildings, which don't add up to 40,000 square feet. And just for perspective, within our program, the average size of these district heat pump systems is well above 1 million square feet. We recently added additional funding to our program in May to make non-system benefit ratepayers eligible for the program. So both SBC and non-SBC paying customers can participate, and that includes state and city owned and operated buildings, and also sites on Long Island as well as affordable housing. We do have a preference within our scoring criteria for project sites that are located in disadvantaged communities or include low to moderate income housing. We have upcoming proposal due dates, one at the end of this year in the mid-November, and then we're planning to run the solicitation through the end of 2023 as well, with 4 additional proposal due dates. So these are the different funding categories, which I've mentioned briefly already. We award up to $100,000 for a scoping study. So this is for a project site to determine whether or not a district heat pump system makes sense, and then to narrow down among the different configurations of district style heat pump systems, which one offers the best value proposition. If a site proves to be feasible for a district heat pump system, then a proposer could come in and be awarded up to $500,000 to do a detailed design study. And then finally, we have a construction category for project sites to receive up to $4 million to build a community heat pump system. So project sites don't have to go through each one of these categories sequentially. If a project site has funded a scoping study on their own, then and they've determined that a district style heat pump system is feasible, then they can propose directly to category B. And likewise for category C as well, if a project site already has a fully formed detailed design. So of the 5 rounds that we've closed out so far in PON 4614, we've awarded funding to 39 distinct project sites. And if you go on our website, you can see a summary of each one of those projects, description of where it's located and the types of buildings that it addresses and the thermal resources that they're investigating, along with some other details. And this is these 4 quadrants here show the scope and breadth of the different types of projects that we're working with under PON 4614. Every building end use you can think of is represented within this matrix of different projects. We're working with existing buildings, we're working with new construction, we're working with single owners on campuses, and we're also working with municipalities to address thermal energy networks among multiple building owners within a community. So what's next for us within our community heat pump systems program is to continue working on these feasibility studies, these scoping studies, and we plan to publish them all online. So we have a handful of projects that are nearing completion, and we're working with the solution providers to finish up their final reports so that we can make them publicly available, and we'll continue to share those results with stakeholders. We're continuing outreach. So we have a few projects within category D, which is a our best practices and guidebooks category under PON 4614. And through those, we're doing charrettes throughout the state to coach and educate municipalities on community heat pump systems and the barriers and how to overcome those barriers to implementation. And last month, on July 5th, the Utility Thermal Energy Networks and Jobs Act was signed into law, which will authorize utilities to own and operate clean thermal energy networks. And they're in the process of identifying pilot opportunities. And if you're planning to attend the conference, the Building Energy New York City conference on the 15th, please stop by and attend the Breaking Ground on Geothermal and Thermal Energy Network session. Our director from the Clean Heating and Cooling team, Donovan Gordon, along with other experts, will be sitting on that panel, and you can learn about geothermal in urban applications. So I'm going to pass the mic over to Raymond.
Good afternoon, everybody. I'm Ray Johnson, the Executive Vice President of Engineering and Construction for EcoSave. What I wanted to do is take this opportunity to talk to you about a project we're in mid-construction of, where we are, what we've dealt with, and ultimately where we're going. The 1515 Surf Avenue project consists of 2 towers. It's multi-family housing, part of which is affordable and the other part is standard. And there's a large, on the first floor is a commercial retail space, so about 11,000 square feet. What's also interesting is the whole site is a bore field that is shared by both towers. So it was a bit of a challenge because typically, or previously, when we were doing bore fields, they're open space, either parking lots or fields or something like that, and that's not the case in New York City. Developer of this project was Elcor. The architect, Studio V, MGE Engineering did all the MEP within the building, and we were the design builder for the geothermal bore field, and really worked in collaboration with the MEP engineer for within the building with the geothermal systems. What should be noted is by doing this project, eliminated 12,000 MVH, eliminated the boilers for a water source heat pump boiler tower arrangement, eliminated the cooling tower, so no gas. The other thing we did, we were able to 60% increase or improvement upon ASHRAE 90.1 2016, and it was done in several ways. And you can see the renderings there. It's right on Coney Island, right by the parks, right across the street, essentially, from Nathan's Hot Dogs. And thankfully, a big part of getting this thing done and making cost effective were the awards that we received from NYSERDA, and hopefully also from Con Ed and their Clean Heat program. Next slide, please. And I apologize for a few eye charts, but I tried to get a bunch of information in, and we'll go from there. The project, because it was stacked, we had a combination of vertical and horizontals. Vertical heat pumps worked out well in the residential areas, horizontal where we didn't, and we prefer the verticals because they're much easier to maintain. What also happened during this project is we converted all the domestic hot water to a CO2 heat pump system that winded up getting certified during the design process. And we thought with CO2 as a refrigerant, and again, very environmentally friendly, higher efficiency, and tremendous advantages. So it was worthwhile, even though we're midstream, to change over to the domestic hot water CO2 heat pumps. We also have dedicated we have DOAS systems, and they're heat pump with heat wheels to serve for ventilation, air, and then to manage. And also we have some interesting heat sinks. We use swimming pool as a heat sink. And another thing to know is that these buildings were cooling dominant, so the domestic hot water actually helps us to level off loads for all the buildings. So we have a bit of a balance. We started construction in 2021, and really the bore field started October, November drilling, and we're essentially in August. We're complete on the underground work. Also should be noted is with this site, we packed in about as much as we could in deep in wells. We have 153. There are 20-foot spacing throughout the site. They're to 500 feet, and it was a bit of a challenge because we've also have to coordinate that with the foundation, with the structural elements and utilities below grade. Next slide, please. Again, I apologize for the eye chart, but a couple of things I've wanted to focus in on this thing are the community heat loops provide scale to reduce installation costs. It's as a designer, as an engineer, or as a designer of systems, we did not have to oversize for worst case conditions as much, so that there are economies of scale that we were able to take advantage of. Secondarily, we have diverse loads, so that enables us not to always reject heat to the bore field or take heat from the bore field, but to transfer it with diversity, with other different peaks from different users. So again, it helped us from the standpoint of optimizing bore field size and reducing costs, initial costs. What also should be noted is that with the bore field, and this is just a geothermal advantage, is that we didn't have to house boilers, we didn't have to house cooling towers, so we've also freed up some real estate for other use, rentable space or whatever. So again, advantageous to the customer. Next slide, please. And here's where I really want to get into when we talk about what our challenges were and where we're going. So as you can see, that site utility plan, or really the foundation tracker, those red circles were all our wells to 500 feet. The yellow and the blue were piles and pile caps. So we had to coordinate, and the coordination isn't just making sure that the wells weren't in the same place as the piles. It was also a matter of, and if you can see some of the pictures, where we're doing this work simultaneously, where you have to coordinate the actual implementation, which could be difficult, and I mean, it wasn't easy, but it really identified to us and how important it was that we coordinated not only final locations of things, but how we were going to do things, how we kept out of the way of other folks, out of the pile driver's way, out of the plumbing contractor, the electrical contractors, with such a tight site. Next slide, please. The other thing is with schedule is, so we're drilling, and so we're in the middle of the winter. We started really in earnest through November, and the site we had to deal with freezing equipment, worrying about freezing piping, getting through things, and that was a bit of a challenge, but ultimately that's what we needed to do. So we learned a few lessons on how to freeze protect the equipment so that we didn't have loss of time or spend as much time early on drilling wells. The other thing that is so important is with bore fields is to know the geology, not only just the conductivity, diffusivity, so that you can thermally size the bore fields, but we've got to know what the soil structure is, what's underground. Is it clay? Is it gravel? Is it bedrock? Is it sand? And what we found, even though with test wells where some of the it was inconsistent in places, and you have to be able to address that. We went through different drilling fluids. We had casings apart. We went through different drilling bits, and ultimately, I think we were doing a half a well a day when we first started, and by the time we finished, we were 2 to 3 wells a day. So, and that was a function of the crews being familiar with this, with the site, and having the right tools going in. So there is, regardless of how much testing you do, there is a bit of a learning curve when doing the well drilling. Next slide, please. So where we are right now is, and again, an interesting part is we have these 150, 350, 100, let's say, wells drilled, and we have to build those into networks. And we're fusing those with horizontal pipes that you can see in the drawings that are below grade. They're fused to each of those wells, caught up, tied up, connected by to the vertical wells, and then once completed, they're pressurized to validate, flushed, and then pressurized to validate the integrity of the system. So what's interesting now is that here we are in August of 2022, and the work for the bore field is essentially, I would say, 90% complete. What remains is for the building to be built. And right now, the building is the 16-story tower is about 6 stories done. The 26-story tower has about four stories done. And there's a lot of work going on, plumbing and other parts. So what we're finding now are some of our pressurized systems. We have hits. We have to repair, redo work. So again, it's inevitable that you'll have some of that. However, what we're trying to do is minimize this, which we're doing, and we've worked with the CM to make sure that happens. But the other thing that's interesting is we guarantee the performance of the system, and we're really not going to know where we are with this until the project's complete and we can do full testing. Currently, we're expecting first quarter of 2024 for this building to be done. But in the interim, we've got a system that has been sized right, has been pressurized, and we're waiting for a building to be completed above it. We'll have the internal of the building piping, the pumps, the heat exchangers, and the heat pumps installed and test the system probably the end of 2023, beginning of 2024. Next slide, please. And here are the things that I would recommend, and it's just things that we've learned, and I got to qualify a few of these. Like, new construction is easier to adopt than retrofit of existing system. That's not necessarily true, but if you have the site that you can have a bore field out that can support a bore field with the outside of the building envelope, outside of the footprint of the building. What we had was a building that were from the ground up, so that we had to use the footprint of the building for a bore field. So it's important, especially in New York, where buildings are so dense that you've got to have the site. So it has been, for the city opportunities, better to do new construction. As you get into more rural areas, that is not as much of a demand. Load modeling for building and bore field, and this is a tricky one. But we model buildings to determine heat loads, cooling loads, and from that we have to size generally boilers and cooling towers and chillers. Well, here that's not the case. We have something that's very is dynamic also, and it's heat transfer between the heat pump loop and the ground. So not only do we have to model the building, we have to model the bore field and how it performs, and ultimately that's going to become an integrated model because we don't really have a second chance. You size the building, you size the bore field, and if the bore field doesn't work, it has to be augmented, and we don't want to do that. So it's imperative that we have a proper model for both. Optimal facilities, low diversity, as we're saying, it's so much better to not use the heat, the bore field as a heat sink or a heat source. Only use that. It's preferable to be able to transfer to other places. So if we're in cooling in one area and heating in another, that's beneficial to everyone. It's so different use groups and on the same bore field is a wonderful thing to have. That being said, that happens, I don't know, less than 10% of the time, and we're transferring heat into or out of the bore field. And what we're trying to do, or we want to do, is balance it on an annual basis so that we don't have creep of temperature of the bore field year after year after year. We want to make sure even though it's seasonal, we reject as much heat as out of the bore field as we put into it. Also, you'll find with it's close in a lot of areas for geothermal. It's important, higher utility bills, places where there's consideration, or people want to be green, want to reduce carbon footprint, want to get away from fossil fuels is absolutely advantageous. And our customer, when we built this, they weren't looking for this thing to be 20% or lower than on first cost as compared to a normal system or a conventional system. They wanted it just to be close, because they understood the importance of ESG, their environmental governance. So and we found that we have a lot more. Our customers are much more environmentally interested in being good environmental stewards. And lastly, district loops are so much better. And we were looking, one of the things that we're looking at in new designs is to have manifolds so that we can go to contiguous properties after something's put in, so that we have the ability to expand the bore field even after the construction is done. So with that, again, my name is Ray Johnson. We've got a project that we're really proud of, and in another year, it's going to be completely operational, and I thank you all. So I'm going to turn it over to Tony.
Okay, thank you, Ray. Hopefully you can hear me. So my name is Tony Amos, Senior Vice President of Endurance Energy. I've been part of the geothermal story for 20 years of my life, and I have to admit that trying to sell geothermal ground source heating and cooling systems has been not the easiest thing to sell, and probably one of the hardest things I've done for the last 20 years. And I've got to say an absolute massive thanks to Donovan Gordon and his team and Sue Dougherty for what I consider to be a rather inspirational incentive that I believe will eventually make a significant change in certainly in New York State, and hopefully other states will see the same sort of solutions, how they make sense. So that's me. Next slide, please, Sue. So having spoken to Donovan Gordon probably 2 years ago, and in telling me about this incentive, it made me realize that I needed to be where the action is. So I actually moved lock, stock and barrel into New York City, and we got a team together, and we went out and tried to encourage developers, most of the developers that we were already talking to, and raise the profile of this PON 4614. And we were probably a lot more successful than even I was expecting. And so we went and submitted 8 projects to NYSERDA, and expecting not to win all of them, but we were very blessed by NYSERDA, and they appointed all of those 8 projects. And I have to admit, it's been a struggle at times to deliver the work, but it's been a great opportunity for us as a business. Ray was talking about a stage C that Sue alluded to for the NYSERDA PON 4614. So we primarily focused on the stage A, which is the feasibility. And we teamed up with MEP Geothermal. And on the regulatory side of it, which features quite significantly in the NYSERDA PON 4614 requirements, the regulatory review of the solutions. So where we are today, we secured these 8 projects in the first round, and it's taken us probably 18 months to get to what we're calling milestone 4, which is the final report. Milestone 1 is what a business as usual would look like. Milestone 2 is basically regulatory review and potential solution. Milestone 3 is an analytical side of it, life cycle cost analysis, that kind of stuff, and the comparison against a business as usual type solution, and the CO2 savings, energy savings, and all that kind of stuff. So to begin with, some of the projects that we looked at range from existing buildings that were being retrofitted, a lot of multifamily buildings, low-income housing. We were involved in a university campus conversion. And in each of those cases, as we do as a team, and I've done for the last 20 years, is the first thing we do is to look at, well, what solutions are most pertinent for this project. And one of the things we look at is obviously the geothermal borehole solution. New build technology, new build solutions might include energy foundations. And looking at Ray Johnson's project there over in Coney Island, I'm thinking, well, why didn't you use the energy foundations, or sorry, the foundations there to reduce the amount of ground loop? Other solutions that we've looked at, sewage heat transfer, becoming increasingly sort of questioned, why we're not using this solution. Looking at using water that's being pumped out of MTA stations. I couldn't believe the amount of water that is being pumped out of MTA stations, even on the driest of summer days, into the rivers around New York City. It's a energy source that's just simply being wasted, and it's running back through the fissures of the rock that supports most of the structures in New York. Just to be pumped out again, just so that the MTA can maintain their train service through New York City. And then we would look to deliver peak loads using air source heat pumps as a solution. So next slide, please, Sue. So what is our methodology and approach to 4614? So the first thing to do is obviously get together with the developer, and the journey needs to include the developer and make sure he's on board at all key stages, and his team as well, mechanical engineering, consultants, architect, gathering all that information, and then looking at what the business as usual might be for that developer, that we can then demonstrate our proposed solution would look like against what he would build as normal. So looking at capital costs, what the utility payments might be from previous projects, what his maintenance costs are for other buildings that he's built recently, calculating carbon emissions, and again, most very importantly, looking at regulatory requirements, additional value streams, possibly the MTA water, and how we can add that into the type of solution. And then exploring the thermal technologies that might be most suitable for that particular project, as I previously alluded to. And then on top of that, can we add solar PV? Can we add a battery energy storage solution? Can we incorporate EV charging as an added bonus on this project? So it's part and parcel of trying to deliver a holistic energy solution. To get to net zero, you're not going to get it. You're not going to deliver it with just heat pumps. You need to incorporate solar PV and some of these other renewable energy technologies to get there. Next slide, please, Sue. So very importantly, establishing the baseline. Next slide. So we go into a lot of detail here because, as Ray mentioned in his summing up of his project, getting the energy model right is absolutely crucial to ensuring that the heat pump solution is sized correctly, ground loop is sized correctly, and then also the distribution to the building is sized correctly, and the equipment that's then delivering heating and cooling in the apartments, commercial areas, retail areas is sized correctly too. So we spend an enormous amount of time at this stage breaking out from the architect's drawings, working with the architects team in this respect to generate energy models. This for me is the kind of the most important piece of the process when you start to develop a geothermal solution. Next slide, please. So what you end up with is a 8,760 hour energy model that's detailing how much heating and how much cooling is occurring, and also what the hot water demand is like. And then from that, you can then also determine, can we deliver simultaneous heating and cooling? So where we're delivering cooling, the resultant heat, some of that can be pushed back into the heating circuits and maybe the heating for hot water. One of the beauties of geothermal systems is that opportunity for that simultaneous load. And that's one of the areas where you're going to end up really pushing the energy savings significantly. Next slide, please, Sue. So the next stage, once we've got all this energy model confirmed and we're satisfied with it, what solution are we going to look at? And Endurant Energy and our partners, we look outside the box, and it could be, obviously there's the tried and tested, and we see 500-foot boreholes being drilled predominantly in the US, but there are other solutions that can be explored. Horizontal ground loops, potentially for universities, schools, lake loops, river loops, extraction wells, recharge wells, MTA type systems. And if it's a new build and foundations are potentially over 60 feet, I would suggest that utilizing the very foundations that the building are sitting on makes for a very efficient solution in terms of the capex, driving the capex costs of this type of solution down. And then obviously what you also see on the roof there is an air source heat pump and potential solar panels. And also perhaps can we bring in heat recovery from wastewater into our solutions too. Next slide. So one of the trickiest areas that we've dealt with is do we go decentralized or do we have a centralized equipment? And again, involving the developer at this stage is very important, because it could be that their general design for their typical buildings might be fan coil units, individual heat pumps in each of the units perhaps. That will dictate the distribution system and can have a significant effect on the capital costs of the type of solution that you're looking at. One of the things that we found was that a decentralized solution in a lot of the new building seemed to make a lot more sense financially in most cases. However, with this kind of system, there's a lot less opportunity to utilize that simultaneous heating and cooling element than there is on the centralized solution. Next slide. I thought there was a central plant option in there as well, but that's not there. Okay. So mechanical equipment concepts. So again, our energy model, what we, over the 20 years that we've been designing these kinds of systems, we would never design a system to deliver all of the heating and cooling from a geothermal system, purely because if you try and design a system to meet those peak loads, you're going to end up with probably 3 times the size of the bore field that you really need. And when you go back to the developer and tell him that what it's going to cost him, he's probably going to say thanks, but no thanks. So optimizing the ground loop system is absolutely paramount. So trying to identify a point at which you can deliver heating and cooling. So if you click on the next slide. So yeah, so we've identified here through our analytics that we can deliver and size a pretty a heat pump, ground source heat pump system that's going to deliver the most energy efficient period here. What's important is making sure what you install in terms of the heat pumps, they're running pretty constantly. These guys don't like to be switched on and off. So we try and optimize it so that we can deliver as much as possible. And then for those peak periods that potentially only occur for maybe 1, 2, maybe 3 weeks of the year, we've got an air source heat pump that delivers those peak load conditions. And then for those really cold days, we might just resort to an electric boiler just to provide a top up, especially for heating for hot water. So next slide, please. Next slide. So yeah, just some of our key findings then from the 8 studies that we've completed so far. So what we've seen on the business as usual, where we've been comparing against gas-fired boilers and VRF systems for cooling, electrical usage increases moderately when displacing gas in new build, and we see CO2 savings increasing by 31%, OPEX savings around 44% for going geothermal. When we compare an all-electric building so an all-electric building might be VRF heating and cooling systems. I'm going to come back to this because what we see here is where we go geothermal compared to just realized I sent you the wrong slides. So it's not business as usual versus all electric. It's business as usual, and that should be bracket all electric building. The electrical usage drops between 44 and 50% on the projects when we compare the VRF air source heat pump systems. CO2 savings dramatically are better by 47 to 53%, and so OPEX savings. So I'm going to come back to this point in a little while. When we look at retrofit and steam, electrical usage dramatically increases by one of the projects by 1,430%, but you can see what it does to the CO2 savings, which is important in this particular project because they were fearing the carbon tax laws that were coming through that would have a significant impact on their buildings. So it made perfect sense. And again, big OPEX savings on over a 30-year period made the system stack up. So if you can go to the next slide. So despite demonstrating to the developers in most of our cases, clean heat incentives play a significant role in making solutions economically viable in New York State. There's some areas like Westchester make it even more viable than other areas. for gas constrained reasons. VRF solutions and packaged thermal heat pumps remain a preferred go-to solution. It's very difficult to persuade the developers to go down a route that isn't the tried and tested route. We're getting a lot of pushback. Some of the regulatory hurdles with district energy systems also seem insurmountable. Crossing over highways and sidewalks is a regulatory nightmare, it seems. One of the developers was quite concerned about that. And heat from sewage, DEP, DEC, obviously quite concerned about the effects on their infrastructure. And there's one bullet point missing off that. Some of the lake and river solutions that we're looking at too, there's a lot of environmental and regulatory concerns, obviously, about that. So if we go to the next slide, which, so yeah, geothermal and VRF comparison. I mean, I'm not going to say a great deal about this, but so capital cost, there's a significant benefit associated with that. One of the projects where they've decided there are these new package units that you can just bolt onto a wall, and you've then not got the distribution through the building, the 2-pipe system or 4-pipe, big savings. But the problem is you've got, as we've identified, is this significant energy consumption associated with these units compared to a ground source heat pump system. We've measured 40 to 45%, as we've alluded to. Carbon savings are far better with a geosystem. You've got VRF, you've got a lot more refrigerant flowing through buildings with VRF systems. Geothermal allows a lot more innovation, and that can be quite important if you're looking for lead points. And from a lot of the analysis we've seen, OPEX for a geosystem makes considerably more savings, largely related to the energy usage. And one of the drawbacks we saw with geosystems is the metering aspect, especially on low-income housing, where heating is basically given free, but then there's how do you measure the cooling? But I think it's not beyond the wit of man to deal with that these days. So with that in mind, this geothermal and VRF direction and pressure, if you go to the next slide, and we see what the Urban Green Council are telling us, if we electrify across New York City, there's going to be a significant problem with the electrification. So are we pushing VRF solutions too much and packaged terminal heat pump solutions? Our study is showing that electrical usage drops between 44 and 50% when using ground source heat pump systems compared to those VRF air source heat pump units. My view is that we need a stick to go with these incentives that says to people, you've got to go down a geothermal route here. You've got to drive the electrical cost down, electrical consumption down as well. On that note, I shall hand it back to Sue. Thank you very much.
Thanks, Tony, and thanks, Raymond. We did have a lot of activity in the chat. I'm just taking a peek now for the first time. So can't promise we'll get to every question, but I'm just going to search through, look for something. A lot of folks putting in where they're from. Thank you. Good variety of attendees. So we have a question here from Mike. Is the and this one's for you, Raymond, is the 1515 Surf Avenue project a passive house design?
To be honest, my expertise is more engine. Here, let me throw my camera on. I don't know if it would be categorized as a passive house. I can find out about it. I do know that the envelope was extremely efficient, and we do have thermomass, and the glass selections were such that we were in that direction. But I don't know if it was categorized. It would be categorized as a that. So what I can do is take an action and respond back to the group. I just want to defer to our architect on that.
Okay, thank you. Yeah, and if we don't get to all these questions in the next few minutes, then we could probably follow up and share responses to the questions that have been put in the chat. So there's a question here. This is Massachusetts is working on a few pilot projects, wondering if New York has any district heating projects that are completed as examples that Massachusetts can point to. So as you heard, the EcoSave project that Raymond was explaining will be done next year, at least the district heat pump portion of the project. There are other projects in New York State. If you look to, and now I'm blanking on the college in Saratoga that has a district heat pump system. That's a great example of how they brought down the number of boreholes that they needed to install by having a diverse set of buildings with different heating and cooling needs. So that's one example. Says, so there's a question here for NYSERDA. Does NYSERDA have resources available to local governments to help them support these projects, navigate the decisions that need to be made around laws, permitting, et cetera, and help them decide if they want to own, operate these as municipal thermal utilities? Are operating thermal networks similar to operating municipal water utilities? So a couple of thoughts on that. We do have support for municipalities. I mentioned very briefly some work that we're doing with PACE Energy and Climate Center, where we're just beginning to roll out charrettes, where we'll be working with municipal officials and other stakeholders to provide education along different tracks related to thermal energy networks. So that's jobs, that's permitting and regulatory issues, that's addressing LMI housing, and a couple of other tracks that'll help these help folks break down the barriers of implementing thermal energy networks. And the second half of that question was, are operating thermal networks similar to operating municipal water utilities? Well, personally, I don't operate municipal water utilities, but conceptually, we would be laying down a network of piping across rights of way in a community in order to deliver water to homes. In this case, water through thermal energy networks would be the medium that we would use to deliver heat at an ambient temperature, most likely around 60 degrees Fahrenheit. So in that respect, it would be similar to how a municipality would operate their water. Question here, maybe more for Raymond or Tony, does the underground piping ever break, crack, reduce performance? How would a break be detected and repaired?
There's a few things there. Have they broke, lost integrity? Yes. As far as the piping, there's been accelerated age testing, so that the integrity of piping is somewhere over 50 years. It maintains its integrity, and really further than that, it's just been tested to that amount. There are no joints to eliminate a lot of, it's all fused piping, so there aren't the joints that are the area where you will see failures. But that being said, when you have a lot of things going on in the same place, there is always the opportunity. I mean, we were talking about it before, where other trades during construction can cut it down or break the integrity. And ultimately, what you have to do is it has to be size so that you can isolate loops, and you're not losing a whole geothermal system when you do lose pipes, you may lose part of it. You have a certain factor of safety in design. You hope not to have that, but if you do, there's you have the ability to maintain the loop.
Yeah, I agree with that. So we designed a system in a ground source heat pump system in the underground stations, the Crossrail stations in London. And one of the requirements there was for a design life of 150 years. And together with the Arup engineers, there's some supporting information that says that HDP, high density polyethylene, is pretty resilient to most things, and would easily live out, survive for 150 years. So it's got the longest polymer to man, I think, as well. So, but I think the design aspect is also important. That if you do have an issue, you don't lose lots of loops. You can isolate localized area. So there's a design component to the system, and then there's the human factor in terms of making sure that you've got the QA QC aspect right on site when these guys are fusing loops, and making sure that you don't have connections too many. You mitigate the joints in the loops as much as possible.
All right, thank you. Yep, and you touched on this briefly, but these are resilient systems. The way the thermal resources are distributed throughout the network allows you to isolate, aspects of the system so that you can perform those maintenance and repairs. So a question here, what factors do you need to take into consideration if a site is 100% residential and you don't have diversity of uses? So I'll let Tony and Raymond chime in after I just share this thought. So through these feasibility studies that we're doing under Pond 4614, that's precisely one of the things that we're trying to tease out from these project sites. So comparing if each building were to pursue heat pumps individually, independently, not connected, versus what if each building was then networked together? Are there opportunities there in the form of reduced costs? So to mobilize a drilling rig for 10 different residential homes that want to convert to geothermal, maybe it's a better opportunity to connect those buildings together. Maybe it's a better opportunity to drill 10 separate boreholes. So we acknowledge that there are situations where an individual heat pump system still makes sense, and I'll let Tony or Raymond add to that if they wish.
You can go first, Tony, if you want.
Yeah, I'm not sure what else I can add to that. That's
so here. I'll just add some. There's what I'd call like an economy of scale. When you have 800 units, your oversizing from a percentage of the total is much lower than it would be when you have 8 units. There's just there's scale on that. The other thing is when you design systems, you're thinking about peak loads, and the more loads on it, the notion of simultaneous peak loads is less of an issue. And again, it allows you to be a little bit more aggressive with design. And then ultimately, when you're talking about different use groups, if the load profile of a residence is much different than the load profile of a hotel or something of that sort, so you're able to take advantage of those things also. And that's kind of are some of the advantages of a community geothermal loop.
Yeah, absolutely. I was just thinking about a project that we did in the UK for Oxford University, where we were designing several buildings as we were going along, but with always with the mindset that we had 2 ports that were sort of heading out of the building, so that when they completed the last building in this one area of the university, the last building wouldn't need any more geothermal loops in the ground, because we could utilize the other 5 buildings to deliver the heating and cooling to that building by connecting all the loops together. Building a data center in amongst residential would be good, because you got lots of heat, being generated, heating for hot water.
Great. Yep, those are good opportunities.
That's that diversity. That's what you're looking for.
Right. Well, thank you both. I see that we're at 2 minutes, and Ben, I apologize, we didn't leave a lot of time at the end for any closeout activities. We do still have a lot of unanswered questions and comments in the chat, so we'll take those offline. And thank you, everybody, for all the questions and the opportunity to speak with you today.
Thank you.
Yes, thank you. And thank you very much, Sue and Ray and Tony. If you would like to put your contact information in the chat so people can follow up with you, feel free to do that. Thank you to NYSERDA for sponsoring today's webinar and also for sponsoring our conference. A reminder that the conference is coming up on September 15th. You can register on our website. And we have one more pre-conference webinar coming up next Friday, September 9th. John Hacker from Daikin will be talking about heat pump inverter technology. So please join us for that as well. I'll put some details and links in the chat. And once again, thank you all for joining us today. Have a good rest of your afternoon.
Thanks, Ben.